Good evening, everyone. We'll wait for 5 more minutes to let others join and then we can start the session. So, good evening, everyone. Welcome back to the PMRF TA sessions. This is week 2. I'll just share my screen. Give me a minute. Am I audible to everyone? Can
Yes,
somebody?
ma'am.
Yeah, thank you. Yeah, can you see the slideshow?
Yes, ma'am.
Okay, thanks. So yeah, so we are having these sessions for NPTEL online course, which is Drug Delivery Principles and Engineering, hosted by Professor Rajat Agarwal from IISc. So we have already, I might have given you an introduction in the last week. So as I said, we are discussing some previous year assignments as well as few key topics which are discussed in the current course. So does anybody have any doubt before we start, or else I'll go ahead? No? Okay. So we'll just go over some of the key points which were discussed in this week 2 lectures. And yeah, so from the first week, we already know what drug delivery is. It's the administration of the appropriate dose or appropriate drug to relieve patients and to cure diseases. And we already know its purpose, that the, the current treatments might have certain side effects, or it might be for a prolonged duration. So to eliminate some of these disadvantages of the current treatment, we are learning about this course. And some concepts about prodrugs, controlled release, biopolymers, and the properties were discussed in the first week. Following this, the course is going towards more in detail about biopolymers. So what was discussed was, it started with natural versus synthetic polymers. Of natural polymers are, so polymers are basically large macromolecules of monomers which we use for biological applications. So these can be natural, which means they can be derived from any biological source, or these can be synthetic. We can synthesize these polymers depending upon our need. And the choice of what exactly to go for in between natural and synthetic will depend upon its application. And then certain desirable properties of polymers were discussed. For example, your whatever polymer you are using, since it's going to be used for biological application, you're going to inject these polymers or deliver these polymers to human patients. They should be non-immunogenic, meaning that they should not have a very adverse immune reaction, otherwise your therapy will fail. They should also be non-toxic. There should be no additional toxicity associated with these polymers. They should be biocompatible. We'll discuss some of these concepts as we go ahead with the questions as well. And what right polymer to choose for your particular therapy will depend upon its application. For example, the route of administration. How are you going to deliver these polymers? Whether you're going to inject them, administer them orally, or you're going to give them parenterally. So not all the polymers will be compatible via all the routes. For example, if you have one particular polymer, it it is very biocompatible when given by an oral route, need not necessarily mean that when you inject it via parenteral route, for example like an IM, intramuscular injection, it might cause toxicity. So you have to know about what is the toxicity levels of your polymer, and if it's going to be toxic via a particular route of administration. Also, what polymer to choose for will depend upon its surface properties. For example, if you want your polymer to have cells adhering to it after you inject it into the body, or if you don't want the cells to adhere, you want it to be completely inert material, based on that, based on your application, you will choose the polymer. Also, what is the load bearing capacity of your polymer, or whether you want the polymer to be biodegradable or not. If it's an prosthetic or an implant, you don't want the implant to degrade, right? You want the implant or the prosthetic organ to remain in the body for a longer time to give relief to the patient. If it starts degrading, then the patient has to undergo surgery multiple number of times. Or in other applications, some of the for some of the application, let's say you are giving a therapy to a patient and you want the therapy to continue only for a year. After a year, you want that polymer to degrade in the body. You don't want another surgery to remove that implant. In that case, you'll go for a biodegradable polymer. So some of these concepts were discussed. Next comes up is the biocompatibility. So what is biocompatibility? It is nothing but the host reaction to polymers. Since these polymers, whether they are natural or synthetic, doesn't matter, they are still foreign to a patient's body. So once you inject it into the body, the host body, the patient's body is going to have some amount of reaction to it. So you can't completely eliminate that. So all our efforts go into minimizing this immune reaction or this host reaction in order to make it more biocompatible. So first of all, to know whether your polymers are going to have any adverse reaction in the patient's body, you have to assess it using different methods. For example, there are certain in vitro assays wherein you in incubate your polymer with certain cell lines, or there are in vivo assays. You can take your polymer and you can inject it into an animal model, for example a mouse, and see if the mouse develops any adverse reaction. In case you see that the polymers are not biocompatible, you can make them biocompatible by certain methods, such as coating, let's say coating your polymer with a very biocompatible molecule, such as proteins that are found in the patient's body, something like that. So these concepts were also discussed. Next is the biodegradability and bioerosion. So bi- bioerosion can be via two different methods. It can be a bulk erosion or it can be a surface erosion. Bulk erosion meaning the polymer or the implant that you have will start eroding from all the sides. It will erode inside out and it will completely disentangle. Versus surface bioerosion is so your polymer or your implant will start eroding from its surface and then gradually it will shrink in size. Next, there are several factors affecting bioerosion, which can be the backbone, how your what exactly is your polymer made of, whether it's hydrophobic or hydrophilic. More hydrophilic your polymer, more faster the rate of degradation once you put it in the body, and whether it's crystalline or it's amorphous. All these factors will affect whether your how fast your polymer is going to degrade, and you need to know some of these things to successfully design an implant or successfully use that polymer for some application. So various different polymers were discussed, for example polyester class, polyanhydride class. Then there's a concept known as polymer drug conjugate, wherein suppose your drug is a very small molecule and you want to enhance its effect, you can conjugate it with a polymer. Now this will provide certain advantages. It can make the drug more soluble. Let's say you have a very hydrophobic drug and you want to use it for some treatment, but it doesn't dissolve in water at all, so your body will not be able to absorb this. So in that case, you can just conjugate your drug with a very hydrophilic polymer such as PEG. That will make your drug more soluble. It can be more stable, it can be more safe, and making this polymer drug conjugate will give you a certain amount of control over its release. Apart from having these advantages, this system might have certain limitations as well. For example, now along with your drug there is another polymer molecule, and this completely changes the drug. It makes it a new entity. So now you have to again prove that this entity is not going to cause any toxicity, it is going to be effective. Because now you have made a new molecule, it will have new regulations. You have to pass through all those regulations for it to get into the market. Also, since now the polymer is conjugated with the drug, there are chances that the drug polymer conjugation has happened in such a way that it might lose activity, because let's say the drug has a specific active site and that's where your polymer is getting conjugated. So because of this, your drug might lose function, so then you have to repeat all this process all over again. And now along with the drug, to sterilize the product, you have to also consider the sterilization of polymer, because your polymer might also degrade at the by the way you're sterilizing this formulation. So all of these things need to be considered when you are making this polymer drug conjugate. And the last topic discussed in this week was controlled drug release. So controlled drug release can be achieved by using various systems. For example, there is diffusion control system, wherein you have a very highly supersaturated drug, concentrated drug in a reservoir system, and because now it's concentrated inside and there is very low concentration outside the reservoir, your drug will flow at a particular rate from the reservoir system to the outside. So in this way you can control how much drug is being released, for how long, for what duration. Then there is solvent control systems, wherein you can have some swelling hydrogels we'll be discussing in the upcoming lectures. So in this system, water will flow inside, it will swell, and because of this swelling your drug will slowly be released from this formulation. And there are certain chemically controlled systems. One example is the polymer drug conjugate. So some of these topics were discussed in this week, and we'll discuss some of these concepts as we go ahead with the questions as well. Before moving ahead towards the assignment questions, does anybody have any doubt? You people can stop me at any moment and let me know. If anybody is writing any messages, I cannot see it, so it's better you unmute yourself and speak if there's a problem. Shall I go ahead with the assignment questions? Okay, I'll move ahead then. So this is week 2 assignment. So the first question is, for a given polymer, we have to rank the glass transition temperature, melting point and crystallization point from lowest to highest. So there are certain options given here, only one option is correct. So take your time in uh, getting at the right answer, and then we can discuss the answer. Anybody wants to volunteer for the answers?
It would be TG, TC, and then TM.
Okay, TG, TC, TM. Okay. We have one answer. Anybody has a different answer or would like to give their opinion as well? Thanks for answering. No more response? Okay, then we'll discuss the answer. Yeah, you were right. The correct sequence is TG, TC, and TM. So, what all of this means, first of all, is TG is your glass transition temperature. It is the temperature at which, just a minute. Yeah, this one. It's the temperature at which a polymer will undergo a transition from your hard glassy state to a rubbery state. Tc is the temperature at which crystallinity appears, and Tm is the temperature at which all the crystalline regions will melt. That is, your crystallinity will disappear. Now, how is this curved? You see a curve here, which is heat flow versus temperature. Now, how do we calculate this for any given polymer? Is you have something known as a differential scanning calorimetry, which looks something like this, the schematic on your left. So herein you have two different pans. One pan will have your polymer sample and one will have your reference sample, and then both of these are given heat flow, and the aim here is to keep the temperature constant of both these pans. In the process of keeping this temperature constant, your polymer is going to either absorb heat or it will release heat, and then we get something like this curve. So we'll go over it one by one. So as you increase your heat flow, this is your specific heat. Specific heat is nothing but the heat you provide to your sample to raise its temperature by, let's say, 1 degree Celsius, by 1 unit. So as you increase the heat flow, essentially first you are going to, you're right now you have a very amorphous solid, you have a very hard glassy state of your polymer. As you increase the heat flow, it and as the temperature increases, your polymer is going to absorb this heat. It will then convert itself from a hard glassy state to a rubbery state, because now you're giving it a lot of heat. So that's where your Tg will appear first. This is the glass transition temperature. Next, as you increase the heat, the temperature will not increase much, because all of these, the polymer chains are now being disentangled because of the heat. Then at one particular point, what is going to happen, because now all these polymer chains are mobile, they can move around a little, they're going to try aligning themselves in a proper ordered state. That's where your, now because this is what is meant by crystallinity. Your crystallinity will start increasing in the polymer sample. As your polymer chains are trying to align themselves in an order, this is an exothermic process, so it is going to release heat. So because it's now releasing heat, you don't need to externally supply it any heat. That is why this heat flow will drop down, and you'll hit temperature which is known as the crystalline temperature, the Tc. As you further go on increasing the heat flow, now your chains which were ordered will now again start becoming disordered, and at a very high temperature, which is known as the melting temperature, all of this crystallinity will reduce, it will decrease. So that's where your Tm is there. So the increasing order of your temperature will be Tg, Tc and Tm, which is the second option is the correct. The glass transition first, then you'll have a crystalline temperature, and then you'll have the melting temperature. Is this clear?
Yes, ma'am.
Yeah, thank you. Okay, then let's move ahead to the next question. Somebody is asking me to tell you about TM. Okay, so TM, I'll just go over this again. TM is nothing but the melt transition temperature. Now your when your polymer has been converted from a glassy state to it's now become very crystalline. So as you still go on further increasing the temperature, further increasing the heat flow to this polymer, eventually it is going to start melting. So all of these crystalline nature that is having crystalline nature means nothing but the polymer chains are arranged in a very specific order. Now to any ordered system, if you further supply heat, it is eventually going to be disordered. Your polymer chains are not going to be in an ordered state and it will start melting. So this is your melt transition temperature, or known as your crystal melting point. Is this clear? Yeah, welcome. Okay, the next question is which of the following statements is not a limitation of polymer drug conjugates? And there are two correct options. So take your time reading through the options. We have to select statements which are not a limitation of polymer drug conjugates. And then we'll discuss this question.
Good evening, ma'am. This is Bhuneshwari.
Yeah.
Polymer drug conjugates can improve bioavailability of many poorly soluble drugs. I think that's not the limitation.
Okay. Okay.
Thank
Okay.
you.
Yeah. Thanks for answering. So you've answered only one. So we are supposed to choose two statements. Okay. Just keep that in mind when you're reading the questions. Even for your exam, wherever you see that you have to choose more than one option, just be careful with these questions. Thanks for answering. Anybody else has a response?
Yes, ma'am. Again, polymer drug conjugates can be made targeted for specific applications.
Okay. Okay. You have the two answers. Okay. We'll wait for if anybody else has another response and then we'll discuss. Others have any answer? No? Okay. We'll discuss this question. Yeah, you were correct. Both the options are correct. So to if you get confused with such a question, what you can do is you can try first looking at what are the limitations of polymer drug conjugates. Once you know that, whatever is remaining is the correct answer. So this is what we were also discussing at the start of the session, that let's say so this polymer drug conjugate can be used for both the system. Let's say your drug is a very small molecule. In that case, what you can do, you can have a big polymer backbone, and to this you can then conjugate your drug molecules. Then, and this conjugation can be water labile or it can be easily broken down by enzymes. So this is one way of formulating polymer drug conjugates. In case you have a very big drug molecule, for example, it can be a protein. What you can do in that case is you can conjugate it with polymer chains on all its sides, and this then imparts certain advantages to this formulation. For example, it will increase in it will make it more hydrophilic, because now your polymer is more hydrophilic. Next, because these chains are arranged in such a way on this protein molecule, it will not allow any immune cells to come around it. It will not allow any immune cells to to engulf this protein, which is what you want. If your immune cells will start engulfing your drug, it won't be any more effective. So these are some of the advantages of polymer drug conjugates. We are supposed to list what are not the limitation. In case what the question is trying to tell you is you have to list some of the advantages of this system. So first is polymer drug conjugates can improve bioavailability of many poorly soluble drugs. As I said, let's say your drug is a very hydrophobic molecule. If you then conjugate it with certain hydrophilic polymers such as PEG, it will increase the solubility, and because now your drug has been made more soluble, it will consequently lead to more bioavailability. Bioavailability is nothing but it is the amount of drug that is actually available at the site of action. Next advantage is polymer drug conjugates can be made targeted for specific applications. So let's say you want this drug to be active at a very particular site. What you can do is you can conjugate it with the polymer, and on the top of this polymer you can, let's say, you can conjugate it with some antibody which is very very specific to a cell type. So in that case you can make a very targeted drug delivery system. Is this question clear?
Yes.
Yeah, thank you. If there are no more doubts, I'll move on towards the next question. Yeah, the next question is, a gold surface was grafted with a polymer. The ends of this polymer are tagged with 4 pendant groups, which are A, B, C, and D. And the pendant groups are weak acids. The modified isoelectric point of the entire polymer were calculated to be as follows. We have been given the isoelectric points. And these particles are loaded with a positively charged drug on the surface using electrostatic interactions in PBS, which is of pH 7.4. Now we have to choose which of the following will have minimum loading. So the question is essentially, you have a gold surface which has polymer over it, and the ends of this polymer is going to have 4 pendant groups, 4 different molecules A, B, C, and D, which are weak acids. And on top of these particles, we are going to load our positively charged drug. Now we have to choose which of these particles will have minimum loading. So take your time in understanding the question. If you know the concept of isoelectric point, I think you will be able to answer it. If not, we'll discuss further. Any volunteers for the answer?
Would it be group A?
Group A, okay. Option 1. Anybody else? Thank you for answering. No one else? Okay, then we'll discuss the answer. So the correct option is answer D. So we'll look at it properly. So what is isoelectric point, which is Pi? It is nothing but it is the pH at which your molecule will carry no net charge. It will be 0 in charge. So we have been given 4 different groups here, 4 different molecules with their isoelectric points, and they're put in a solution of PBS, which is of pH 7.4. Now if we want to see which will have minimum loading, we know that our drug is positively charged. To have minimum loading, your group should also be positively charged, because then positive charge will repel each other, and as a result there will be very less loading on the particle. So to know that, we need to see which of these groups A, B, C, D will be positively charged at this particular pH 7.4. Now we know by a rule that if your pH is less than your isoelectric point, your molecule is going to have positive charge, and if your pH of the solution is more than the isoelectric point of a particular molecule, the molecule is going to have a negative charge. All of you know this concept, right? Because in acidic pH, most of your the COH groups or the NH3 groups will be all protonated, because there is more H plus in the solution, so that's why your molecule will have a positive charge. And versus if the acidic if the pH is very basic, it means there is very less H plus ions in the solution. As a result, your molecule will start deprotonating. All your COH groups will be COO minus, so they'll leave the H plus. As a result, your molecule will have negative charge. Now here we want to see which of our molecule is going to have positive charge at that particular pH. So from, if you see the isoelectric points of all A, B, C, D, only D molecule which is having an isoelectric point of 9. Oh sorry. So at this pH of 7.4, your molecule D will have a positive charge. Is this making sense? Because your pH is less than the isoelectric point of this molecule. As a result, it will have a positive charge, and because this positive charge will then repel with the positively charged drug, as a result of which there will be very less loading on this particular particle. Am I going too fast, or are there any doubts in this? Is this clear?
Yes, ma'am. Sure.
Yeah, thank you. So most of you are answering, I see, but since I'm in the PowerPoint mode, I'm not able to look at your answers. It's okay if even if you chat, or if you want to say out the answer, you can just unmute yourself and give off the answer. Okay, clear? Shall I move on? Okay, then we'll discuss the next question. Okay, next question is, which of the following are correct with respect to PLGA particles? This is again a multiple choice question, so more than one answer is correct. So we have to choose two correct options regarding PLGA particles. So read through the options, take your time, and then we'll discuss.
Option 2 and 5.
Option 2 is it can be used as a vehicle, and 1, 2, 3, 4, 5. This one, it is not a copolymer. Okay, so one answer is option 2 and 5. Anybody else has any other answers? No more response? Okay, no issues. Yeah, so yeah, we are supposed to select correct options regarding PLGA particles. So one of your answer was correct, whoever answered. The last one is not, so we'll discuss. So let's look at the options one by one. It is a non-biodegradable polymer, which is false, because PLGA easily is a very biodegradable polymer. So this option is incorrect. It can be used as a vehicle in gene therapy. Yes, it is used. You can for gene therapy, you have your DNA and or an mRNA particle, which you can encapsulate in PLGA particles. So it can be used in gene therapy. Next is they can degrade at gastric pH. Yes, so PLGA hydrolysis can be catalyzed by acids and bases. So this PLGA hydrolysis can occur just with water, or if there are any acids or bases present in the solution, they will further increase the rate of this hydrolysis. So PLGA hydrolysis can be catalyzed by acids and bases. And since gastric pH is very acidic, it's somewhere around 1.5 to 2, your PLGA is going to degrade at gastric pH. So this 2 and 3 option are correct. We'll look at the other options as well. They have not been used clinically, that is false. PLGA is approved by FDA, so it is very well established into the drug delivery field and it's routinely used. It is not a copolymer is also false, because PLGA is a copolymer of two different polymers. One is polylactic acid, one is polyglycolic acid, so it is essentially a copolymer. And last option is they can be extracted from chitosan based products, which is false. Chitosan is a natural polymer and PLGA is a synthetic one, so you synthesize it. So the only two correct options here are it can be used as a vehicle in gene therapy and they can degrade at gastric pH. Is it clear?
Yes.
Okay, thank you. Okay, then I'll move on towards the next question. Next is, what are the advantages of using polyethylene glycol, which is PEG, in drug delivery application? Again, there are two correct options. So read through the options carefully and we have to select advantages of PEG. Somebody trying to answer? Sorry, I couldn't hear you. Any volunteers? Are you trying to answer?
Option 2 and 5.
Okay, 2 is non-toxic and 5 is 1, 2, 3, 4, 5, can deliver cargo. Okay, thanks for answering. We'll look at the answer shortly. So we have to select the advantages of PEG. Anybody else, or is your mic just on?
Option 2 and 4.
2 and 4, okay. Somebody is answering 1 and 4. Okay. Yeah, we'll look at the answer. Thanks for answering. We'll look at the correct option. So first is has well developed conjugation chemistries. We'll go over the options one by one. So first is has well developed conjugation chemistries, which is one of the advantages of PEG, because it's very easily tunable and people have done a lot of research in this. You can conjugate PEG with a lot of antibodies, you can conjugate it with proteins, very different. You can conjugate it with a number of small molecules as well. Next is non-toxic, immunogenic, can be produced under GMP. So I think there's some mistake with this option. It should be non-immunogenic. So it's non-toxic, very well biocompatible with the human system. It is non-immunogenic, which is not actually, so there are some PEG antibodies being reported in few of the studies, but they are not very harmful. So you can consider PEG as non-immunogenic, and it can be produced under good manufacturing practice. This is very important because then you can easily scale it up and use it for developing your drug delivery system. Now the rest of the three options are highly hydrophobic and biocompatible, which is false. It is not hydrophobic, it's actually hydrophilic. That is one of the reasons why PEG is used in a lot of applications. Next is it can be easily phagocytosed by immune cells, which is also false, because we saw in this particular system where you have these PEG chains. So because of this a number of PEG chains being conjugated with this particular drug molecule or a protein molecule, it will not allow your immune cells to come anywhere near the drug. So it is not easily phagocyted. Which question were we on? So yeah, it is not easily phagocytosed by immune cells, and since it is not very easily phagocytosed by immune cells, it cannot be used for delivering your drug intracellular very efficiently, because then since your immune cells or other cells will not be able to take this up because of these the nature of these peg chains, we won't be able to deliver the cargo inside the cell. So the only two correct options are the first two. So people who answered various different options, I hope it's clear now.
Yes, ma'am.
Yeah, thank you. Okay, no more doubts here. Then I'll move on towards the next question. Next is, if a particle takes time t to diffuse Lmm, how long will it take to diffuse 4 Lmm? So this is kind of a very short numerical, and we have various different options. So take your time in calculating this. Sorry?
64.
Okay, 60/40. Okay, we have one answer. Thank you for responding. Anybody else? Somebody saying 2t. Okay, we have another response, which is the first option. Any other answers apart from 2t and 60/40? No? Okay, then I'll discuss the correct answer. So the correct answer is 16t. We'll look at this. So this question essentially is based on the concept of root mean square displacement. This tells us how long or for what distance is your molecule going to diffuse once you know its diffusivity. So this root mean square displacement has a formula of root 2 dt. So this is the same molecule uh, that we are discussing. So essentially your diffusion coefficient is an inherent property of your molecule. So that is not going to change here because it is the same particle. Then all you have to do is you have to put these values into this formula. Let's say first you have been given this value that to diffuse Lmm it is going to take t time. So you just write L is equal to root 2 dt, and next we have been asked that if it now needs to diffuse to 4L, that is 4 times the previous distance, how long is it going to take? So if you just put all these values here and if you solve this, you will get something known as the answer is 16t. So that is 16 times the time of the previous in the previous case. So this essentially tells us that if you want to go 4-fold, your time is going to increase 16-fold. That is a square, because this root mean square displacement is root of 2 dt. That means your time is going to be squared. So if you have previously you had L distance, you had t time. If you have 4L, it's going to be 16t. Is this clear?
Yeah.
Okay, thank you. Okay, somebody has asked me about hydrophobic and hydrophilic. We can discuss this at the end of the assignment. I'll come back to your doubts. We'll first go over all the questions. Sorry?
Can you repeat the question? This one.
This one? Okay.
Oh, yeah.
Okay. So here we know that, so we have been, the question is, if particle takes time t to diffuse Lmm, which means we have been given a distance and we have been given the time it takes to travel this distance, and then if it wants to travel a distance of 4L, it wants to diffuse 4L, which means 4 times the previous distance, how long is it going to take? So this is based on root mean square displacement. It tells you how your molecule diffuses in a system. So the formula is root 2 dt. So your d is your diffusion coefficient. Here in this particular case, your particle is going to be the same in both the cases. So your diffusion coefficient is not going to change. So you just put all the values in this formula. For the first case, you have L, distance is L, then your time is capital T. Now if you want to solve for the small t, we want to solve for how long is it going to take if your distance increases to 4L. So you just put all of these together. You don't need to know the actual value of this diffusion coefficient because it's going to get cut. So if you just solve this, squaring both of these equations, you'll get time as 16t. So 16 times the previous time. Is it clear now?
Yeah, okay, thank you, ma'am.
Yeah, welcome. Yeah, as I was saying, I'll come back to the doubts later on, which you guys have posted in the chat box. We'll first go over all the questions. So I'll move on towards the next question. Next is reservoir system refers to, and there are several options which talk about reservoir systems. We have to choose the correct one. Take your time reading the options and then we can discuss.
Option 4.
Option 4, 1, 2, 3, 4 systems which are non-degradable membrane are super saturated with a drug. Okay, we have one answer. Anybody else?
Option 6.
The last option, systems with a semi-permeable membrane which degrades with time. Okay.
Option
Others?
C.
Option C, all systems with first order. Sorry?
Last.
Last option. Okay. Any other answers? So far we have 4 and 6.
Option A.
A is a system saturated with drug surrounded by degradable membrane. Okay. Anybody else? Thank you all for responding. No? Okay, we'll discuss the answer. So the correct answer is systems which have non-degradable membrane and are supersaturated with drug, which is option 4. I think one of you answered correctly. So let's look at what a reservoir system is. So this is basically one of the diffusion controlled systems which we were talking earlier. So a reservoir system is defined as it is a supersaturated drug reservoir which is surrounded by non-degradable polymer membrane. So what you have is you have a drug core. This is the loaded drug which is very super saturated at a very high concentration, and then you have a polymer membrane over it which is non-degradable. So the only way for your drug to be released from the system is diffusion. So when you inject this, you formulate this in such a way that you have a control over how much concentration you have put here. You have a control over this polymer membrane thickness or its pore size. So as you inject this, your drug is slowly being released out of this system because of its diffusion coefficient or its diffusion phenomenon, because outside this polymer membrane there is no drug, inside there is a very high concentration. So naturally, because of Fick's law of diffusion, your drug is going to be diffused from this supersaturated area to towards the outside. So the options are a system saturated with drug surrounded by degradable membrane, no. A reservoir system, the only reason it's called reservoir because it's like a depot, it's a storage where your drug is stored. So if you have a degradable membrane, then your drug will be released at a very high rate. And if your membrane starts degrading at a very faster rate, all of these supersaturated drug might come out at the same time. So that is not what we want. We want a controlled release system. So in this case, this option is incorrect. Then all systems with zero order release rate, no, not necessary that this should have a zero order release rate. Or all systems with first order release rate, again not necessary that they will have a first order release rate. And then we have systems which are non-degradable. This is the correct option. Fifth was all systems with second order release rate. No, there is no second order release rate here. And last is systems with a semi-permeable membrane which degrades with time. Again, we don't want our membrane to be degradable. So the only correct option defining reservoir system is systems which have a non-degradable membrane and are supersaturated with drug. Is this clear?
Yes.
Okay, thank you. If there are no more doubts, I'll move on towards the next question. I think I have one last question. Yeah, this is the last question for today's assignment. The question is, which one of the following polymers degrades hydrolytically by near zero order kinetics? So we have been given different types of polymers and we have to know which one is going to degrade hydrolytically, which means by water, and will have a zero order kinetic.
Option number 3, polyanhydride.
Polyanhydrates. Okay. Thanks for answering. Anybody else wants to give it a go? Option C. Yeah. Okay. Both of you have answered the same thing. Anybody else has a different answer? No? Okay. Yeah, both of you are correct. The correct option is polyanhydrides. So polyanhydrides have surface erosion because they are very water labile. They have very highly water sensitive linkages. So because of this, the your polymer is going to start eroding only from the surface. As a result of it, constant rate of release, because it's degrading only from the surface. So if there is a constant rate of release, it does not matter how much drug you have inside this polymer. So that is why it will have a zero order kinetics. Is this clear? I think that's the last question I had for today's assignment. So there are a few numericals. Okay, I'll stop presenting. There are few numericals in this assignment as well as the previous assignment, but since you guys have still to submit, I think the deadline for you to submit both of these assignments is 7th or 8th August if I'm not wrong. So I still can't discuss the numericals with you. These are the same ones. So I'll discuss it in the next session if you guys are interested in solving or discussing some of these numericals. So that's all I have for you today. I think somebody had a question. Yeah, somebody had asked how to know if you're still here. I think it was, I don't remember the name. Somebody had asked how to know whether your polymer is hydrophobic or hydrophilic. So this you come to know from the structure. For example, let's say you have PEG, which is polyethylene glycol. Since it's a glycol, it will have a lot of OH on its surface, which is a hydrophilic functional group. As a result, your PEG is going to be a very hydrophilic molecule. On the other hand, if you have, let's say, PLG is made by lactic acid and glycolic acid. So you should be knowing the structures of this to know the properties of your polymer. So for example, let's say lactic acid has a methyl chain, that is a CH3 chain, which is a hydrophobic functional group. So as a result, your PLG is going to be hydrophobic. So if you just compare both of these head on, PEG and PLG, your PEG is going to be more hydrophilic compared to your PLG. So that's how you know about the hydrophobicity or hydrophilicity, depending upon the structure of your polymer or the backbone, what bond it is connected with. I hope I have answered your question. If you have any other doubts, we can discuss. If not, then we'll meet in the next session where I'll be discussing few numericals from the first and the second assignment. If you people have any doubt with the current assignments, we can discuss that as well. Only after you have submitted it, of course. Or any other doubt in the sessions, you can go ahead. Welcome. People who have doubts can stay back and ask later on if you want. Others can leave the meeting. That's all I have for you today.
Can you repeat the last question, ma'am?
The last question? Okay, wait, I'll share my screen. This one, which one of the following polymer degrades hydrolytically by near zero order kinetics? So yeah, so the answer was polyanhydrides, because polyanhydrides are very highly water sensitive, so they undergo something known as surface erosion, which is let's say you have a polymer coating over some of your drug molecules, so they will be eroding from the surface because it is highly water sensitive. So your rate of erosion from the surface will be more than its bulk erosion. They'll completely start degrading from the surface. Now because your polymer is degrading from the surface, so it does not matter how much amount of drug you have inside the polymer. Since it's degrading from the surface, it will have a very constant rate of release, and which is known as zero order kinetics. So polyanhydrides are one of the polymers which degrade hydrolytically by near zero order kinetics. So you can use these to formulate some of, if you want a constant rate of release.
Thank you, ma'am.
Yeah, welcome. Anybody else wants me to repeat any question? If you guys have joined late, we can go over the assignment questions again. If not, I'll see you guys in the next session.
Ma'am, could you explain the isoelectric pH again, ma'am? That
Okay.
second question, I think.
Yeah, I'll just go over it. I think it was the third question. Yeah, this one. Okay, so you understood the question, right? We have a polymer which has 4 different functional groups, and on the
Yes.
top of this polymer we are going to load our positively charged drug. So what we have
Okay.
been asked is which of these will have minimum loading. So now if your drug is positively charged, to have minimum loading, your polymer, whatever functional group is there, this group should also have a positive charge, because then positive will repel and it will have minimum loading. So the only information we have with us is we have the isoelectric points of all these functional groups, and we also know the pH of the solution.
Okay.
So essentially what isoelectric point is, it is a point at which your molecule will have no net charge. It means it is the pH at which your molecule will have no net charge. So if the isoelectric point and the pH of the solution match, your molecule will have a zero charge. Now below the isoelectric point, if you go below isoelectric point, pH of your solution is below isoelectric point, your molecule is going to have positive charge. And if the pH of the solution is above your isoelectric point, the molecule is going to have a negative charge. Now to have a positive charge, we need to look for the group which will have a isoelectric point that is higher than the pH. So the only molecule here which has it is molecule D, that is having a isoelectric point higher than the pH. If you have molecule A, its isoelectric point is below the pH, so it will have a negative charge. Same for 5.5, this molecule B. If you choose molecule C, it is the isoelectric point is same as that of the pH of the solution, so it will have a net zero charge. Versus if you see the last molecule, it has a very high isoelectric point, so so it will fall somewhere under this, right, this class, where your pH is less than your isoelectric point. 7.4 is less than 9, so your molecule will have a positive charge, and because of this, since your drug is also positively charged, it will have minimum loading.
Okay. So the drug with sorry, ma'am. The polymer with the pH 7.4, that will have zero charge, right?
Yeah, it will
when the
have
pH
zero
is
charge.
equal to-
Yes, your
Okay.
polymer
So again, it will be minimal. Again, the coating will be minimal.
Yeah, so let's say you have a completely neutral molecule, and on top of that you are loading positively charged. Versus if you have a positively charged surface, on top of that you are loading positively charged drug. So the positive repulsion will be more. You're correct. So the highest loading will be for A, then it will be for B, then it will be for C, and then it will be for D.
Okay.
Yeah. So some amount of loading you can expect for this C molecule, but the minimum loading will be for this molecule D.
Okay. Thank you.
Yeah, welcome. Anybody else has any doubt or wants me to repeat? So this video will be uploaded in YouTube, as well as I'll be uploading the PPT as well if you want to go over it once again. And if you still have doubts over this, we can discuss in the next session as well.
Ma'am, could you please upload the PPT in the last week?
Yeah, it's
Session, ma'am.
uploaded. So I forgot to give access to everybody. It's uploaded in the
Okay.
in the folder. You people
Oh.
have access to both the YouTube links and the folder, right? If you're not able to
No, ma'am,
access,
I
you
don't
can let me know. I'll check again.
have. Okay, ma'am.
Yeah. So I'll just post my email ID in this. If you have any doubt, you can email me. Yeah, let me know if you don't have access. I can give that. Nobody else has a doubt? Shall I end the meeting then? We'll meet next Monday. Thank you. Okay, then see you people next week if
Thank
there
you.
are no more doubts. Yeah. Thank you.
Thank you.
Thank you, ma'am.
Thank you.